the agenda for this session is as shown on this slide. To begin with, for the benefit of those who are not familiar with LLVM Libc, we will give a very brief introduction to LLVM Libc. Next, we'll move on to the core part of this talk, which is a detailed presentation of the status of the development of LLVM Libc. We'll talk about all the Libc functions that we've implemented. We'll talk about the loader that has been built. We'll also talk about the various pieces of infrastructure we have built to support Libc development. After that, we will briefly talk about some of the challenges we faced and explain how we have overcome them. Finally, we'll finish the talk with a quick presentation about the future outlook and talk about what we would like to see done in the next 1 year or so. Let's get started. So, what is LLVM Libc? It is a greenfield Libc being developed under the LLVM umbrella with a certain set of goals. We also have a list of features we would like to see in this Libc. For example, we want this Libc to be built in a sanitizer-friendly fashion from day one. We want the Libc to be implemented in the C++ language without any assembly code. Typically, in other popular Libcs, assembly code is used as a workaround for performance problems in compiler-generated code. With LLVM Libc, we don't want to take this route. We want to fix the compiler rather than use handwritten assembly code. Another very important goal we have is to build the Libc in a modular fashion. This modularity is to serve two main use cases. The first use case, if someone is bringing up LLVM Libc on a new platform or architecture, they should be able to do it in a gradual fashion. The second use case, if someone wants to use only parts of LLVM Libc, they should be able to pick only those parts and get the rest from another Libc of their choice. In other words, we want the ability to mix LLVM Libc with other Libcs. There are a few other features and goals also, but to avoid spending too much time on just this topic, I will point the audience to the Libc proposal available under the community-wide proposal section of the LLVM doc site. With that small introduction to LLVM Libc, let's move on to the core part of this talk. So, with the grand list of features and goals in mind, we kicked off the development of LLVM Libc a year ago. Since then, over 10,000 lines of code have been written. There have been more than 200 commits affecting the Libc directory by 17 different contributors. We now have implementations of more than 100 Libc functions. Later in the talk, I'll go over the full list of functions that have been implemented. We have built the beginnings of an ELF loader with the idea of building a fully functional static PI ELF loader in the near future. I will also talk about the loader in more detail later in the talk. We have built the build and test infrastructure supporting the development of the Libc. I will also talk about the various pieces of infrastructure in detail later. Lastly, not the least important though, we have set up continuous integration builders connected to the LLVM build bot. Let's now look at all the functions we have implemented. We'll start with functions from math.h. As you can see on the slide, we have implemented a large number of floating point functions. Barring a few functions, most have been implemented by taking advantage of C++ templates. We have built a utility of template functions to uniformly handle the float, double, and long double variants. So, say for an operation like round, we do not have separate implementations of round, roundf, and roundl. There is just one implementation, a template implementation of the round operation. Internally, the C round, roundf, and roundl functions call this template function. You must have noticed that the list on the slide also includes few single precision, exponential, and trigonometric functions. These functions are based on ARM's contribution of the code from their ARM optimized routines project. Next up are functions from string.h. As you can see on the slide again, a large number of functions from string.h have been implemented. I would like to make a special note about our implementations of the memory functions like memcopy, memset, and b0. The approach we have taken is to optimize them for the statistically more significant subset of inputs. By profiling real-world applications, we obtain the size distribution of the inputs to these functions. For example, we found that 96% of calls to memcopy are with input sizes less than or equal to 128 bytes. Likewise, 91% of calls to memset are with input sizes less than or equal to 128 bytes. So, our implementations are tuned to perform the best for input sizes less than or equal to 128 bytes. Next, we'll look at functions from threads.h. We made a start with respect to building the standard threads library, the one defined in the standard threads.h header file. Some of the mutex and thread functions have been implemented, and patches adding condition variable functions are currently under review. All these thread functions are currently in Linux only, but we plan to port them to non-Linux platforms very soon. There is a reason why we have chosen to implement the standard threads API instead of, say, stdio.h or stdlib.h API. The implementations of mutex and threads are undoubtedly going to be platform dependent. So, implementing a thread library helps us understand the various pieces of infrastructure we need to put in place for such platform-specific implementations. No doubt that implementations of parts of the stdio API are also going to be platform-specific. But threads have an added complication. They are tied to the loader. The loader sets up the TLS of the main thread, and so the other threads also have to set up the TLS in the same manner. So implementing threads.h gives us an opportunity to learn all possible complications beyond just the infrastructure needed for the platform-specific pieces. All right, so moving on, signal.h. We have made a start with a number of functions from signal.h. As with functions from threads.h, they are currently Linux only. In fact, in some cases, Linux on x86-64 only. And again, as with functions from threads.h, we plan to port and extend them to non-Linux, non-x86-64 platforms in the near future. Next are functions from ctype.h. We implemented all functions from this header file, but only for the default locale. Some miscellaneous functions now. We are on to the last slide about functions. As you can see, we have implemented a number of utility functions coming from various header files. These functions were chosen because they help implement other functions, and in some cases, they help implement parts of the test infrastructure. As listed on the slide, we have implemented abort, assert, erno, and _exit for Linux. We made a beginning with an implementation of fwrite also for Linux. We implemented the POSIX mmap and munmap functions. munmap is used to clean up the thread stacks on thread termination, and mmap is, of course, used to set up the thread stack on thread creation. Let us now look at the status of the loader. By loader, I'm referring to the files like crt1.o, rcrt1.o, and other similar object files on Linux like ELF platforms. For those not familiar with these files, or not familiar with the loader in general, one can roughly view the loader as that piece of the C runtime which starts and terminates an application. When you run an application, loader is the one which gets control first. After performing certain housekeeping tasks, it then eventually calls the main function of the application. We made a start with a very simple implementation of an ELF loader. We implemented just enough so that we can use it to set up tests for the thread functions and set up integration tests. In the near future, our goal is to build a full static pi ELF loader for Linux to begin with, and we'll port it to other platforms as we progress. That brings us to infrastructure. We will start with build infrastructure. LLVM Libc is part of the LLVM project, so naturally, our build system is based on CMake. We have implemented a number of custom CMake build and test rules suitable for the Libc. We consider these rules as one of the core components which help us achieve the goal of building a modular Libc. Compared to the rest of the LLVM project, we have done something different, especially with respect to target names. The names of the targets listed via the Libsy specific rules have a Python-like fully qualified name. For example, the target for the scinf function has the name libc.src.math.scinf. This name reflects the path under which the implementation of scinf lives within the Libc tree. We believe that this kind of naming convention makes it easy to understand what exactly a particular target is about. This is especially convenient when reading the list of dependencies of a target. Moreover, when listing the dependencies of another target, say a target that you are working on as a developer, one can deduce the names of the dependency targets in a structured manner without having to look through multiple CMake files. A more important benefit of this naming convention is that it avoids target name pollution. One can list their targets without worrying about the name collision with other targets within the Libc tree or in the rest of the LLVM project for that matter. Moving on, we have implemented a number of utilities to aid in the development and testing of LLVM Libc. Let me start by talking about the unit test framework. At the very beginning, when we had just started the development of LLVM Libc, we started with gtest for the unit test, just like the rest of LLVM. However, we soon ran into conflicts between headers from the system Libc, which are pulled in by gtest, and the headers from LLVM Libc itself, which are pulled in by the Libc implementations and their unit tests. The only foolproof and neat way to get around this problem was to build a custom gtest-like unit test framework for LLVM Libc, which we did. Though this unit test framework is implemented in C++, it does not pull in the system Libc headers or the C++ standard library headers, directly or indirectly. This was made possible by another utility library which we implemented. This library contains a small number of standalone C++ utilities to support the unit test framework and the rest of the Libc implementation. Note that I said it is a standalone C++ library. By standalone, I mean that it does not depend on the C or C++ standard library. It is a header-only library with almost everything being a standalone alternate to an equivalent piece from the C++ standard library. It does not even depend on the C++ runtime. Next among utilities is a template library of floating point operations. I've already talked about this when I talked about math functions, so I will not spend more time on it now and move on to the next utility piece we built. And it is a wrapper library to the GNU MPFR library. In LLVM Libc, we use this wrapper to set up unit tests for our math functions. It helps compare the results produced by LLVM Libc math functions with the results of equivalent functions from MPFR. We set up MPFR to perform computations at a much higher precision, much higher than the 128-bit floating point format. This allows us to verify the results produced by LLVM Libc within a sub-ULP precision of the MPFR results. The reason it has to be a wrapper and not used directly in the unit test is because, as a wrapper, it helps avoid pulling in the system Libc headers, which might come in indirectly from the MPFR headers. Let's now talk about the next big piece of infrastructure we have built. One of the drivers behind the pick and choose kind of modularity of LLVM Libc is built around a novel header generation scheme. The various standard specifications, like the ISO-C standard and the POSIX standard, are encapsulated in TableGen files. For each platform, the list of functions relevant to that platform are listed in another TableGen file called the API file for that platform. One can view this API file as the configuration file for the platform. The header generation tool reads this API file and generates the header files with only the API listed in that API file. The standard specifications captured in the other API in the other TableGen files help this header gen tool declare the functions with the correct signature. This header generation screen is illustrated in a diagram form on this slide. The API file is in the center. Note that the public header files like math.h, they do not live in the source tree. Instead, we have a def file. In case of math.h, this file is named math.h.def. This file lists commands for the header generator. You can see in math.h.def that the command name public API is listed. This command tells the header generator that it has to insert the public API as specified in the API file of the target platform in the generator header file, which is math.h in this case. I have given a very rough, high-level overview of the header generation scheme. For a more detailed description, you can look at the relevant documentation in the docs directory of the Libsy tree. Moving on, client ID checks. The next piece of infrastructure we have built are the LLVM Libc specific client ID checks. They were obviously built to assist developers maintain the overall health of the Libc code. They help maintain the code implementation standards, like alerting developers about the inclusion of undesired headers. LLVM Libc is the Libc itself, so it should not include headers from the system Libc. One of the client ID checks fires if a header file from the system Libc or any other unacceptable header file is included. Another check fires if any part of the Libc implementation ends up in a non-Libc namespace. To avoid name pollution, we want the entire LLVM Libc implementation to be under the namespace __LLVM _Libc. So this client ID check fires if it finds code outside of this namespace. All of our client ID checks are now integrated into the build system. This means that developers are alerted about the deviant code at development time. Additionally, these checks also run on the public CI builders. This helps catch bad code which slips past, say, code review. Next are redirectors. One of the concepts we built for enabling the mix with other Libc's feature is the notion of redirectors. Redirectors are essentially wrapper functions implemented in LLVM Libc which intentionally call into the system Libc. They're normally used when an implementation of a Libc function is not yet available in LLVM Libc. In a world where everything, including the Libc, is statically linked into the application, redirectors might not be of great interest. However, for platforms where a Libc is linked dynamically into the application, they provide a way in which new adopters can gradually switch over to LLVM Libc. Redirectors can also be helpful in another scenario. There are certain functions whose implementation can potentially call other Libc functions. If the callee functions are not available in LLVM Libc yet, then the author of the caller function can choose to use redirectors for the callees. That brings us to challenges. All right, let's now talk a little bit about challenges we faced. I've actually talked about most of these points earlier in the talk, but not really as they being challenges for us. For example, having the ability to mix with other Libcs is a challenge in itself. Will it not be possible to mix everything unconditionally? We want this to be the case for as much of the Libc as possible. The challenge this poses immediately is to understand and define what we actually mean by mixing LLVM Libc with other Libcs. We soon realized that the answer would vary depending on the target platform. For example, what is a Libc on a BSD, right? So before we define what we want or what we meant by mixing with other Libc in a general fashion, we decided to start development on Linux to actually learn the answer to that question for Linux. We now think that for Linux, we have a good understanding of this. The other problems, which I've already touched upon these in earlier slides, like header file mix-up, symbol mix-up, namespace pollution. Well, the solutions again are like having our own unit test framework, having client ID checks which catch namespace pollution, bad namespaces, and even bad header file inclusion. Next, we have even to get the mix with or modular Libsy development going. We have also invented the header generation scheme for modularity and the pick and choose ability. We have very carefully crafted our build rules so that it is straightforward to pick and choose the functions of interest from LLVM Libc. We've also developed the notion of redirectors, as I've explained earlier. The combination of the header generation scheme, the build rules, plus the redirectors give us many ways to pick and choose from LLVM Libc now. All right, so that brings us to the last slide of this talk, our future plans. LLVM Libc is far from being a complete drop-in replacement for other widely used Libc systems. A natural goal then is to complete it as soon as possible. However, with a system as vast as a Libc, we would like to work with smaller goals bounded by a relatively shorter time frame. So I have here a list of items we plan to do over the next 1 year or so. This by no means is exhaustive though. In fact, I will consider it as a minimal list. Let me go over that. We want to complete the math library. That is, we want to have an implementation for all public functions declared in math.h. Likewise, we want to complete the null-terminated strings library, the functions from string.h. We want to implement the stdio API at the least for Linux. We would love to make it cross-platform, but at the least, Linux. We want to set up public CI builders for non-x86, non-Linux platforms. We want to finish the implementation of the full static PI elf loader. We want to complete the standard threads library from threads.h, at least for Linux. We want to set up infrastructure which will help us compare and understand how LLVM Libc implementations differ from implementations of other Libcs. This is especially important for math functions. We also want to run Libc's first targets on OSS first. We have a few first targets already in the source tree. We want to add more of them and then run them all on OSS first. Again, I would like to point out that this is not a minimal list and not an exhaustive list. If there are interested contributors who would like to work on topics not listed here, they are of course welcome to send in their patches. All right, that brings us to the end of this talk. Thank you for tuning in.
Hello, everyone. Welcome to the Q&A. My name is Paula Asker, and I'm here with Siva Chandra. We're going to look at a few questions here. Siva, about the comparisons and migration scenarios for GNU Libc, do you think you could talk about that a little bit?
Yes. So at a very high level, I'm tempted to say that there shouldn't be any difference. Both are Libcs. But I think the proof is in the pudding. And coincidentally, we are kicking off two parallel efforts internally at Google. One is to migrate to LLVM Libc from glibc. The other is to migrate to LLVM Libc from Muscle. So we might learn more about this. And if we think that there are learnings which would benefit the wider community, we'll definitely document them and surface them in some manner publicly.
All right. What code-based analyzer did you use for your statistics on the uses of memcopy and others?
Okay, so primarily, these were Google's internal code bases. I was not directly involved in this work, so I'm not sure if I can say much more than that.
Right. How modular do you believe LLVM Libc will be? For example, you wouldn't want to mix one libc's malloc with another's free.
Yeah, that's right. So I would think that there will be groups of functions that would evolve, like file-related functions and allocation-related functions. And we would, at some point, make it clear that if you want to pick this function, then you'll have to pick the other functions also. Yeah, I would think that's how we're going to evolve as we go forward. We'll be building out cut sets and making it clear, like the build system should make it clear, like if you pick only this, you'll have to pick these also, so I can't build anymore. We'll build infrastructure which helps with picking groups of functions.
Gotcha. Will LLVM Libc include POSIX API that aren't part of the C standard?
Yes, I think we already have a few examples, like memmap and memunmap are POSIX functions. So we will be doing that for platforms where they're relevant, like on Linux, they're relevant. So we have added memmap and memunmap for Linux.
Given there are already several C libraries, how do you plan to increase the adoption of Libc?
That's a marketing question. Okay. I would let the Libsy do the marketing maybe, but there are several C libraries because I think each one tries to fill a gap which the other one isn't filling. And in a way, LLVM Libc was also started to fill certain gaps. So I would think that users who care about the principles on which LLVM Libc is being built would naturally gravitate towards LLVM Libc. I don't see me doing any proactive marketing, at least in the near future.
All right. What is the timeline you believe until at least one operating system is fully supported?
Fully supported, I mean, it's hard to define what fully supported means, but I would like to aim, I would like to see how large applications like Clang, for example, do with LLVM Libc. How can they run just off of LLVM Libc, or are they still pulling pieces from glibc or other libcs? In that sense, I would think for Clang to run off of LLVM Libc completely, it is probably 2 years out. I don't know if I'm being optimistic here, but 2 years out seems realistic to me.
Gotcha. You mentioned your approach is to optimize the compiler rather than hand optimize the code. What do you think this process will look like?
We have not gone through this exercise yet, so I can only give some speculative outlook. For example, we do have examples in the math functions where we think that compilers can do better, especially when they're aware of some of the native instructions. So the process I would think would be like this: like we will go implement something in pure C++, put it out there in the real world, and see how it is doing performance-wise. If there are any problems, then we'll come back and look at how we can improve parts of our implementation using help from compilers. But again, this is all speculative. We have not yet gone through this exercise, so this is all just speculative.
All right. Will the Pi loader come to Windows as well someday? Will it use PE and COF then?
Again, I'm tempted to say yes. If it is really relevant for Windows, yes, then we will one day build a file loader for Windows. And if PE and COF, if it has to support PE and COF, then yes, PE and COF it will be.
All right, next question. Can a Libc be used as a replacement for glibc for cross-compilation? Or sorry, yeah, toolchains to make those GNU-free?
I think this is kind of related to the earlier question. Again, I don't know how to define GNU-free, but the goal is definitely to build LLVM Libc enough that it can be used as a drop-in replacement for glibc or for any other popular libc for that matter.
All right. If Libc is assumed any usage for FFIs, and if yes, which constraints would you define for that?
I've seen this question earlier, and I've seen similar inquiries at other places, but I'm not very clear how FFI relates to Libc. Probably the question is more about what happens if a custom ABI is being used. Will the Libc support it? I think at that point, you need to recompile the Libc for the custom ABI and relink everything. And as I said, I'm really struggling to see how FFI relates to Libc on a day-to-day basis. So this is all I can say at this point. Yeah.
All right. Are there any plans to add performance benchmarking for Libc?
Yes, there are plans, and we already have built some infrastructure for benchmarking memory functions like memcopy, b0, and memset. And the plan is definitely to widen this to many other functions from the Libc, especially the math functions.
All right. Would the redirector work in a bare metal environment?
That's an interesting question, but I think it will be more of a case-by-case basis. Is there a dynamic loader available on bare metal? Because it assumes that the system Libc is being linked in as a shared library, so you need a dynamic loader. If it is, then yes. But if there is no dynamic loader, and if the bare metal system platform is only cares about static linking, then you wouldn't really need redirectors. You could just use linker semantics to mix LLVM Libc and the other system Libc you have.
All right, so we're running a little short on time, so this will be the last question. Do you maintain a list of already implemented and missing features that could be turned into a Libc status page?
That's a good suggestion. We don't have it. And yeah, so as I mentioned in my answer for another question, we would like to pick few representative applications. And instead of having a list of functions which are there and functions which are not yet there, we would like to surface information which showcases whether how much those representative applications are using from LLVM Libc and how much they are using from the system Libc. Basically a relative comparison, like how well is this application, how well is LLVM Libc ready to support this application without having to pull pieces from the system Libc.
All right, well, thank you so much for answering our questions. There will be a roundtable later, as I understand. So thank you so much.